Hi everyone, this is Gao. I'm Assistant Professor of Medical Engineering at CalTech. It's wonderful to be here virtually today to share our recent research on skin interface wearable biosensors. Long-duration space missions pose important health concerns for astronauts. These include microgravity, radiation, inadequate food and nutrition, and cognitive or behavior conditions, especially stress, anxiety, and depression. How can we monitor the health condition in deep space? One of the promising approach would be wearable sensor, and in general, for healthcare in Earth as well, wearables can play a very important role in personalized healthcare because they can continuously collect data from our body and tell us what's going on and what's going wrong with our health. But if you look at what is commercially available health monitors, Apple Watch, Fitbit, there are some smartwatch designed for special use, as I can see. However, all these commercially available health monitors, they can mainly track the physical activities of vital signs. They cannot provide more useful information about our health at the molecular level. We think a major gap, which is also a great opportunity in this field, is how can we collect physiologic information at the molecular level, ideally non-invasively. In this regard, we are looking at an important body fluid, human sweat. Sweat can be retrieved from the human body completely, continuously, and non-invasively. It contains a number of important analytes or biomarkers, including electrolytes such as sodium, chloride, potassium, calcium, metabolites such as lactate, glucose, urea, uric acid. We can also identify a number of different types of amino acid, vitamin, hormone, protein, or peptide. Of course, we can also see different types of heavy metals and drugs or other substances from our human sweat. Imagine that if we could develop a wearable sensor that can analyze our sweat biomarkers from the skin, we could use this type of information for fitness checking, for disease diagnosis, and very importantly, the large set of data collected from our daily activities can be used for numerous new fundamental and clinical investigations, especially when we couple the molecular data collection with the physical data collection. We run big data analysis or machine learning. We could use this to develop a number of different predictive algorithms toward preventive care, which can be very important for future personalized health care. In 2016, I published our first work on fully integrated wearable sweat sensor for in situ multiplex sweat analysis. This fully integrated system can perform real-time in situ monitoring of multiple metabolites, including glucose and lactate, multiple electrolytes, including sodium and potassium, as well as the skin temperature. The system can perform on-site signal conditioning, processing, and wireless transmission. So eventually, all the data collected by the phone, collected by the sensor, can be sent to the cell phone through Bluetooth wirelessly, and we can read the analytic level from a custom-developed cell phone app. So as you can see, this is a fully integrated system. It consists of flexible sensor patch that can be replaceable, disposable, can be prepared at larger scale and low cost using printing technology as well. So it consists also a flexible PCB board. This is a reusable part. It takes several seconds just to replace the sensor patch with a new one to make sure we can get reliable data over time. There are many other leading experts in this field, including Professor Joe Wang, my postdoc advisor, Professor Ali Javi, and Professor Jason Hackenfield from Cincinnati, and Professor Dion Kim from Seoul National, and Professor John Rogers from Northwestern Universities. Together, this field is moving forward pretty quickly. Very recently, we developed a large-scale, low-cost manufacturing approach to fabricate wearable biosensors. As you know, because sweat sensor is facing consumer use, if we want to apply our technology for large number of people, we want to make sure the sensor can be mass-produced at low cost. And if we want to detect low concentration biomarkers in human sweat, usually people need a nanomaterial. But modifying nanomaterial, people usually do drop casting manual operation. which can cause larger sensor variation. That's why using this approach, we propose this laser engraving approach. We can use a CO2 laser engraving to fabricate the graphene structure on the polyimide surface. This graphene structure can be controlled. The morphology and property of the graphene can be controlled by controlled laser engraving parameters. So based on this graphene, we can fabricate high performance, highly sensitive chemical sensors to analyze biomarkers in human sweat. We can also develop graphene-based physical sensors to monitor temperature or strain. Strain information can be used to extract respiration or heart rate. So we could also use the laser engraving to fabricate microfluidics. When in the microfluidics, when new sweat come out, we want to make sure the new sweat can push away old sweat. Our sensor can analyzing the fresh sweat, and in this case, our sensor can also have miniaturized influence from sweat evaporation because everything is done in the microfluidics. So in summary, we use laser engraving. We can patent multimodal microfluidic sensor patches that can perform high performance chemical sensing, high performance physical sensing, as well as highly efficient microfluidic sweat sampling. So the lead author Isabella recently received the Forbes 30 on 30 in science because of this work. Our group are mainly focused on developing a wearable system. Not only we develop sensor, from chemistry or material innovation point of view, we also develop systems. We want to make sure we can build a reliable wearable system to collect data from the people's daily activities. That's why, as you see some examples of integrated system, we can package the sensor as a wristband, headband, or bandage like a sensor patch on the skin. During the physical activities, we can collect the molecular information continuously from the human body. We also do sensor validation using the gold standard using HPLC, GCMS, ELISA, depending which type of target that we are looking at. We want to make sure our sensor can provide accurate and reasonable readings from the human body. Till now, some people may have a question. Since we are doing sweat sensor, so what if I don't have sweat when I do exercise? What if some people, many patients, they cannot even do vigorous exercise, right? How can we make sure? It's a very good question. How can we make sure our device can be broadly used by most people? We have to address this problem. How to access sweat sample without exercise or beyond exercise? How can we apply this in the clinical settings? From literature search, we found that sweat can be induced through a process called interdisciplinary. How this works? In a clinical setting, people use this small equipment to apply a current between the two electrodes, hydrogen-loaded electrode. Current flow will deliver the positively charged drug molecule below the skin. It could be pyrrocarbon, for example, could be methacholine or acetylcholine. They can stimulate your sweat gland, trigger local sweating. Basically, you apply some time current, deliver drugs. Drug will trigger the local sweating. Then you can use the doctor will use such microdata sweat collector to collect sweat samples. They can send out this sample to a laboratory to perform chloride tests. This is for cystic fibrosis diagnosis, one classic application of sweat test. So inspired by this process, we developed a new wearable platform that can perform on-demand sweat extraction and sensing. So basically, we incorporated a miniaturized interdisciplinary module on our wearable sensor. So everything can be controlled by the cell phone. If we want to do sweat analysis, we can click button from the cell phone. We can start interdisciplinary mode. Basically, a small current can apply on the wristband, for example, for several minutes. After this, the drug will stimulate sweat gland and trigger local sweating. The continuous sweating process can last for a long time, depending which type of drug or which drug doses we are using. The sensors can perform real-time sweat tests during this period. As you can imagine, this is very attractive for many biomedical applications, especially for those people who don't often do physical exercise, for people with patients in the hospital, or people work in the office, they don't do vigorous exercise usually. In collaboration with the Stanford School of Medicine, we actually characterize the sweat induction process. We applied different type of drugs or drug dosage to control the sweat induction process. As you can imagine, if we use different type of drug or drug doses, many parameters of the sweat induction can be changed. If you look at this curve, response latency, look at one parameter. If we use pyrocarbon, the red bar, 240 seconds. After applied current, sweat come out a decent red after 4 minutes. But if we want faster, we can use ethylene column 10%. You see the sweat coming out within 1 minute after you apply current, which can be very efficient. Such on-demand sweat extraction and sensing platform allow us to perform a number of different types of clinical applications. So I want to share with you some example applications we have done. First one is disease diagnosis. I just briefly mentioned earlier. Cystic fibrosis is a genetic lung disease. Clinically, the diagnosis of CF is based on sweat tests, basically sweat chloride. The doctors will collect the sweat using the nanophoresis, using their small equipment, send out this sweat sample for a laboratory test, which could take a week to get a chloride level. As you can imagine, this is very time-consuming. In collaboration with the Stanford Cystic Fibrosis Center, we have applied our device on healthy people and on CF patients. We found that, it just takes 20 to 25 minutes, including sweat induction and sensing. We can reliably analyze sweat sodium and chloride from healthy people and from patients. If you look at the statistical value, the patient level are much higher compared to healthy people. Considering that the gold standard for CF diagnosis on adult individuals, sweat chloride higher than 60, we can say that our device can be used for screening and diagnosing cystic fibrosis in this case. Another application is that we can apply our wearable sensor for metabolic monitoring. One example is gout management. As we know, gout is the most common inflammatory arthritis affecting tens of millions of people worldwide. Gout is characterized by chronic hyperuricemia. Basically, we have high uric acid level. And too high, the uric acid level will crystallize near the joint, will cause a lot of pain. For the gout patients, they cannot eat too much red meat, shellfish, or beer, because they will very easily trigger gout attack. So for the healthy people, gout is mainly induced or developed because of the lifestyle or genetic reason. So monitor uric acid could be very important for healthy people to minimize the chance for developing gout. For gout patients, it could help them to really minimize the potential for gout attack or chance for gout attack. For the people on medication to lower uric acid level, the uric acid concentration collected by the sensor can be used to guide their therapy or medication, how much drug to take to lower the uric acid level. So overall, it could be very beneficial. We have applied our laser engraved microfluidic sensor patch to analyzing sweat uric acid level. We recruited, male subject, female subject. We see that during the fasting period and after pure-rich food intake, sweat and serum concentration of uric acid show very similar trend. We also recruited gout patients with gout, subject with hyperuricemia, as well as healthy people. We compare together in collaboration with our clinical collaborator, Professor Jiang Tsai, and also Professor Zhaoping Li. Dr. Li is the Chief of Clinical Nutrition at UCLA. We found that the patient with gout has both high sweat uric acid and serum uric acid level compared to healthy people. And if we track one subject over a 7-hour period, you see that sweat uric acid follow closely the serum one. If we plot the correlation together, we obtain a high correlation factor between 0.864. Between sweat and serum uric acid level is pretty high already, we think. We are also working on to monitor a number of different other metabolic syndrome risk factors for early diagnosis or nutritional intervention. Another application is that we can use these sweat biosensors for stress monitoring. As you know, like stress is related to many health conditions, including cancer, cardiovascular diseases. Of course, they're more relevant to mental health, mental disorders such as PTSD or major depressive disorders. But stress, the diagnosis of stress or quantify of stress is very difficult. Right now, mostly based on questionnaire. As you can imagine, this can be very subjective. So we are thinking about looking at biomarkers for stress. One of the most well-known stress biomarker would be stress hormone cortisol. If we can quantify cortisol, we can potentially quantify stress more accurately. But if you draw blood to analyze cortisol level, that's also problematic because blood draw itself is stress-inducing. And if you want to monitor stress by introducing stress, which is problematic, right? So ideally, a non-invasive cortisol analysis would be very attractive. In this regard, we're looking at sweat cortisol level. So our team recently developed a telemedicine-based biosensor, point-of-care biosensor for rapid access analysis of sweat cortisol level. Our cortisol sensor is based on laser engraved graphene. We use this laser graphene electrode along with the competitive immunoassay strategy. We can quantify cortisol very rapidly in body fluids such as sweat and saliva. The incubation time can be as short as 1 minute. So validated the sensor reading with ELISA, we found that a very high correlation factor, as you see. That means our sensor can provide accurate assessment of both sweat and saliva cortisol level. So we also looked at the correlation between sweat, saliva, and serum cortisol level. You see morning, afternoon cortisol level in serum, saliva, sweat show very similar pattern. So I forgot to mention before, cortisol level in our body follows circadian rhythm in our blood at least. So in the morning, usually we get a high cortisol level. In the evening, low cortisol level. Every day is like this. The pattern of cortisol is very important. It's closely related to many health conditions, including PTSD, depression, and even diabetes. So we actually found that sweat cortisol also follows circadian rhythm. From one subject, you see 6 days. Every day we see morning cortisol level is higher than PM. And we get a very high correlation factor between sweat and serum cortisol, around 0.87. Pretty high already. That means the sweat cortisol can be a non-invasive source for stress quantification. To further evaluate our cortisol sensor in monitor dynamic stress response, we have applied different stressors in human subjects. Firstly, we tried aerobic exercise, which is a strong stressor and induce sweat as well, as you can imagine. We indeed observed the rapidly increased cortisol level in human sweat analyzed by our biosensor. We also see that when subjects stop biking or exercising, the cortisol level starts to drop. We see similar trend in blood as well in this case. We also tried another stressor called the pressure test. Basically, put your hand into ice water, you will feel a lot of pain and a lot of stress. We also observed the rapidly increased cortisol level. In this case, nanophoresis was used to induce sweat. So overall, our telemedicine sensor can rapidly analyzing cortisol level in our body non-invasively, as you can see, and working closely with the Translational Research Institute for Space Health, we are applying our in general wearable sensor platform for dynamic stress monitoring. We can incorporate our physical sensor, chemical sensor, along with this telemedicine sensor. We try to apply machine learning to really classify the stress levels overall, potentially for the deep space stress monitoring of astronauts. The last part of my talk, I want to briefly introduce our recent work on how to power future wearables. When we talk about more and more applications, that means we want to incorporate more and more sensors. It also means high power consumption down the road. So one challenge coming into our mind, how can we power future wearables? Right now, most time we are using a lithium battery, a rechargeable battery, but recharging the battery is not everywhere accessible. So ideally, the future wearables could power themselves by harvesting energy from the human body or from the environment, right? Since we are working on sweat sensor, sweat already contains a high number of biomolecules. That means also potentially chemical energy, right? Can we harvest energy from human sweat? The concept of using biofuel cell to harvest energy from our body fluid has been reported. We are thinking about there are many challenges if to power real wearable device. Firstly, biofuel cell usually cannot provide high enough power. The other way is their stability, long-term stability can be an issue. And for wearables, we want to power the entire system from sensor, from circuitry, and from communication point of view. That means a lot of power consumption. We did a very interesting innovations. I'll talk in the following slides. For the first time, we developed a battery-free biofuel-powered soft electronic skin that can perform multiplex sweat analysis, perform the signal process circuitry in the power. Basically, the whole biofuel cell harvest can also power Bluetooth communication. So the entire multifunctional e-skin can be powered by biofuel cells without using any battery. How we can achieve that? So for the biofuel cell design, we have used from 0 dimension to 3-dimensional nanomaterials. So basically on the 3D nickel structure, you see we coated the surface with graphene and coated the graphene surface with the carbon nanotube. This is for the anode. This increased the active surface area by 3,000 times. For the cathode, we are using platinum cobalt nanoparticle decorated carbon nanotube network. So overall, we get a very high surface area, very high catalytic activities. We can get from raw sweat up to 3.6 milliwatt per centimeter square continuously. This is very high power, 3.6 per centimeter square, milliwatt in this case. This get high power is not good enough. We want to make sure the biofuel cell can be very stable for a long term. That's why we found that the typical biofuel cell can suffer from a short lifetime because the cathode. The cathode, if you use platinum can be poisoned. And if you use a silver-based counter, which is consumable, cannot last long either. So we introduced here platinum cobalt nanoparticle decorated CNT. Cobalt dopant, the transition metal, could enhance cohesive energy, can stabilize this nanoparticle in body fluid. And we further coated the surface with a graphene film. Overall, you see, if you only use platinum, within 1 hour, the performance works very quickly. If you use platinum cobalt, it's very much improved here. If we couple platinum cobalt with graphene film, we get nearly unchanged performance over hours of operation. Here 15 hours, even we store another 24 hours, we can use another 15 hours here. Show very similar performance over time. We can apply this battery-free e-skin to continuously collect the biomarker level from our body. Here we demonstrated that we can use this for urea and ammonia monitoring. We can use this for glucose and pH monitoring. So it's a battery-free system. We can continuously collect this type of information. Recently, in collaboration with Professor Azita Imami, an electrical engineering professor at CalTech with expertise of integrated circuit design, we developed a miniaturized IC chip at the size of 1.06 by 1.32 that can harvest energy and basically perform the energy management and wireless communication. If we couple this IC with our BFC electrode, the overall entire package system is 5.5 by 6.2. They can provide a reliable power output in this case. As you can imagine, in the future, we can really incorporate more sensors and like a kind of biofuel electrode with this miniaturized circuitry. The entire wearable system can be miniaturized still. We are hoping to build a fully self-powered miniaturized wearable system for multifunctional application. The last example is we can also not only use the biofuel cell to power our wearable sensor, we can also use body motion. In this case, we take advantage of a flexible printed circuit board based freestanding triple electrical nanogenerator. So this is we call it FTNG. This is a mass-producible approach. We use standard commercial FPCB manufacturing approach to fabricate this highly robust FTNG platform that can harvest energy from mechanical deformation. So we can convert mechanical energy to electrical energy. Using similar concept as the biofuel cell, we still developed a fully battery-free system that can be entirely powered by the body motion. We can power multiple sweat biosensors as well as signal pulses, circuitry, and Bluetooth communication without using a battery. So, of course, we can also combine different approaches. Let's say do a hybrid system that can rely on both biofuel and human motion. In this case, in all scenarios, we can make the sensor work. To summarize, we have developed this wearable sweat sensor platform that can be used to analyze in different types of biomarkers in human sweat. The large set of data collected by the wearable system can be used for numerous new fundamental and clinical investigations. In the end, I would like to thank my team, my one of group members who made this happen for this most of the work. So I would like to also thank our collaborators and also clinical collaborators, of course, and our funding supports. Thank you very much for your attention. I'll be happy to take questions. Thank you.